Hello and welcome to my video lesson 1.3 on the conservation of linear momentum. Normally, momentum would be conserved unless acted on by outside force. So in a lot of our situations, we're going to be talking about a non-frictional situation, like a rolling ball. A pool ball has very little friction. There will be some, but we'll just assume no friction. Or we can be in a vacuum when we do this, or on ice when we do this. But basically, momentum is conserved unless there's another force. Okay, so perfect conservation of momentum is nearly impossible. In a vacuum, inside an inertial frame of reference, i.e. no gravity, we can get close to that. Even a vacuum is not a perfect vacuum, but we can get pretty close. Okay, so the concept is simply that the initial, I'm going to say the sum of all the initial, this symbol here means sum. So the addition of all the initial momentums is equal to the addition, again sum, of all the final momentums. I put a F there for final. You could also use this prime symbol, but that's basically just meaning final. Okay, so the sum of the initial equals the sum of the final, or another way to say that is delta P. Well, delta P is, just by the way, delta means final minus initial. So delta P is 0 in a conservation of momentum situation, which ends up meaning the same thing, because to move the PF or PI over, right, PF then must equal PI if we move that over. So it means the same thing as before. So we normally would write it like either like this, or simpler, normally we kind of skip ahead to this statement. Okay, so really that just means all the initial equals all the final. Let's move on. So to solve a conservation of momentum question, we follow the following steps. We draw the situation often with a vector diagram, label the masses and velocities before and after, determine if they stick or bounce apart after the collision, create an equation, final equals initial. So this is the big idea here, and then solve for the unknown. So often if we have multiple masses, we need to separate out the different equations. So yeah, here we go. This is example 1. Let's do a couple of these. We have to zoom out just a tad bit more. I think that's probably enough. We just need, one more. Okay, so while playing ice hockey, Leon Draisaitl starts with a speed of 5.56 meters per second and absolutely creams Matthew Tkachuk, who is 93.4 kilograms. I Googled those values as of whenever I Googled them. That is as accurate as I could get. With an open ice body check. Since they are on ice, we can assume the momentum is conserved, although yes, there will be friction. Assuming Tkachuk was stationary to begin with. So, if all that stuff is the beginning, the setup to the question, here is the question. If Leon was stopped after the collision, how fast is Tkachuk moving afterwards? So, kind of like this hit here, he hits him, and then all of his momentum is transferred into Matthew Tkachuk. So, how are we going to write this out? So this is going to be P of, instead of doing like Leon or Draisaitl or Matthew or Tkachuk, we're going to call this player A and player B. And then we'll talk about Leon and Tkachuk later, Matthew later. So, so P of A initial plus P of B initial equals P of A final plus P of B final. So all the sum, the addition, of all the initial momentums equals all the sum, the addition, of all the final momentums. So what you're going to see here is we're going to be able to get rid of some things. So first of all, Tkachuk was stationary to begin with. So Tkachuk is stationary to begin with, meaning his velocity is 0, therefore his momentum is 0. This is 0. Okay? Also, Leon is stopped after the collision. So Leon is stopped after the collision. That is 0. So with those two things in mind, it's going to be PAI equals PBF. So that's now our new equation. Now we can write this out as MAVAI. So that means the mass of the player A times the velocity of the player A initial equals MBVBF. That means the mass of the person B times the velocity of the person B final. Okay, so we're looking at what are we looking for? We're looking for how fast was Tkachuk moving afterwards. So we're looking for this guy. So what we're going to do is move the MB over. So we're going to go like this. MAVAI over MB equals VBF. And now all we have to do is to type this in our calculator and solve it. Okay, so all we're going to do now is type this into our calculator and solve it. Here it is. So mass of Draisaitl, 94.8, times by the velocity initial of Draisaitl, 5.56 meters per second, which I googled. These are roughly speeds that they could be going at. I don't know if they go at this speed when they do a body check, but let's pretend they do. I couldn't Google that answer. So here it is. That tells us that Tkachuk leaves at 5.64, and we're going to leave it just there. 5.64 meters per second, getting launched that speed there. Okay, so similar sort of thing for the second part, or part B of this question. Similar sort of setup. Let's try it again. You can pause the video now, by the way, and try it out for yourself, and then press play and see if you get the same answer that I do. So PAI plus PBI, but in this question, they get tangled up after, together. So you could certainly do them separately for the second part. And actually, I'm going to write it separately to start. Okay, but when we write it down in our next step, first of all, yes, Tkachuk was still stationary to begin with, so that's still 0. So PAI equals, but in the second portion, if they're tangled up, I'm going to call this PTF for total. You could also call it PABF if you want to instead, but I'm going to do TF. That's just the way I'm going to show that. Okay, so what we're going to do now is MAVAI, similar to the last question, MT for total, VTF. So we're going to just give it a little bit of space here. And now we're going to, again, realize that we're solving for their speed, their collective speed afterwards. So we're going to get MAVAI over MT equals VTF. And just keep in mind that MT is the mass of both added together. So I'm just going to write that differently, MA plus MB, because it's both together. There you go. So that we can see it while we're plugging it in. So I'm going to make a fraction. And we get 2.80 meters per second. So if they tangle up together, they basically go half the speed. Not quite exactly, but roughly half the speed as before. Okay. Let us continue. We've got one more different question here. I recommend you pause the video and try it out yourself first to see if you can do it. Otherwise, Once you're ready, press play and see if you get the same answer that I got. Sometimes pool balls bounce off one another. The white pool cue ball is 6 ounces or 0.170 kilograms, while the black one is 5.5 ounces, 0.156 kilograms, so slightly smaller. If the white ball is moving at a velocity of that much to the right, and the black ball is moving that much to the left, they come in at exactly opposing sides and leave at exactly opposing sides. If the black ball bounces back at going 0.9 meters per second, what is the velocity of the cue ball after the collision? So, the white one's going to the right. That's a little bit thick, hey? Okay, that one's going to the right. The black one over here is going to the left. They collide and they bounce off going in other directions. So originally this is 0.8 meters per second, and originally this one is 0.4 meters per second. We know that the black one bounces back going 0.9. So the question is, how much does the white ball bounce back? Okay, so let's go ahead and start trying to solve this. So basically we're going to start the same way. I'm going to say W for white and B for black. So it's going to be PWI plus PBI equals PWF plus PBF. So initial must equal final. Okay, if we know that the white ball comes in, we know its mass and velocity, and we know the initial mass and velocity of the black ball. We also know the final velocity and mass of the black ball. The only thing we don't know is the momentum of the white ball, which will help us get the velocity of that one. So we're going to rearrange this to solve for the momentum of the white ball final. So it's going to be PWF equals PWI plus PBI minus PBF. Basically, we've just moved the PBF over to the left-hand side by subtracting on both sides. Okay, now we can plug this in with all of the different momentum. So MW VWF equals MW VWI plus MB VBI minus MB VBF. Okay, pretty good, but we want to solve for the velocity. Whoops, that's not what I wanted. We want to solve for the velocity of the white ball final, so we're going to solve for that by dividing by MW on both sides. So it's going to be MW VWI plus MB VBI minus MB VBF, whoops, over MW. Okay, so we have now solved it algebraically. Let's go ahead and try to show this on the calculator. I want to make sure we have enough room so you can see the equation. I'm going to just zoom out a little bit. That's what I'm going to do. Okay, so this should be a fraction with MW, which is the weight of the cue ball, times by the initial speed, which is 0.8, plus the mass of the 8 ball, which is 0.156, times the velocity initial, which is 0.4. Yes, we made a mistake here. Just writing it in. It's negative. I'm going to put that in brackets actually. Bracket negative 0.4 because it's going to the left. So just keep that in mind. The directionality matters. Now minus MB, which is the mass of the black ball, 0.156, times by the speed of the black ball, which is 0.9, and that's to the right. So going to the right. So there you go. And then the mass of the cue ball, I'm just making sure that that's correct. Okay, yep. And so now we can solve for that. And we're going to have an answer of negative 0.39. Negative 0.39 meters per second. The negative tells us it's going to the left. So it's 0. And because of sig digs, we should actually just have one sig dig. So 0.4 meters per second left. Alright, so I hope this video helps you better understand some linear momentum questions, and good luck!